Continuing our journey with slope fields and particular solution equations, and we're going to look at type 2 and 3 differential equations. And by the way, that might be a differential equation for type 2 of the form dy dx equals f of y. It's a function of y, okay? And type 3 may be expressed in the form of dy dx equals f of y times g of x. Sometimes you might see that expressed as f of x comma y. Okay, so we have both x and y apparent. We're going to look at two examples. I'm going to show them with the use of technology. Of course, I'm going to describe what it would take, of course, to do them without technology. You need to be across both approaches, okay? Perhaps you may be asked on an exam one day to do a question by hand, or you may want to, in class one day, do one by hand and verify it with the use of technology. So it depends. Here we have an example which is a type 2. Sketch the slope field for the differential equation of dy dx equals y on 2. So we have an f of y type function there, and it gives us essentially a domain and range limit for the size of our grid. Okay. Now on GeoGebra, I just want to let you know that I'm using this slope field plotter, and the authors are visible there on the screen, and it's quite a good application. So I'm going to use that. We've got the required function entered in there, so you can see my cursor hopefully near the window. I've actually made the domain and range a little bit bigger than what the question was asking for, just so you can see it. And I'm just going to turn that off. And basically, when we're looking at this, there's a couple of things here. We have basically y over 2. We don't have an x apparent. So I wonder what color this is going to be. It's yellow. All right. I might just switch that over to a better color. And we have y over 2, and x does not affect the gradient. Okay, so x does not have any bearing on the gradient here. So you can see that as for a certain value of y, let's say y equals 1, as we change x, it has no effect on the slope. So these slope lines across here, hopefully you can see my cursor, they're all the same, and that's for any value of y, any given value of y, the gradients are the same. So we have all across the same gradient. To work out the gradient, we simply use substitution, and of course for all the ones along here we have y equals 1, so we'll have a gradient of a half there. Alright, and then we have y equals 2, so we have a gradient of 1, which is a 45-degree angle. And then we have 3 over 2, which is 1.5. Okay, so it's increasing as we go, and of course that's a little bit beyond what the question asked for there. Okay, negatives, it works the same, except for we'll have, when y equals negative 1, we'll have a negative a half down there. You can see it's a falling line, and so there'll be a fall of 1 per run of 2. Okay, or there's a fall of a half per run. Now, because we have the 2 in the denominator, there are no places here where it is undefined. Remember, when it's undefined, you'll either see a gap. Okay, there could be a gap. Some graphs show a gap, or it could be just a vertical line like so. This one doesn't have any. All right, now I'm going beyond the question again, but if we had a particular solution, we could show that on this one and be fairly straightforward. So let's say you were given the extra information when x equals negative 2, y equals negative a half. You could make sure the solution curve, the particular solution, remember these are graphs of a particular solution, that would have to run through that point there, and as you took it along, you would follow the behavior according to the field, and we can see this curve gradually increasing as we go there. So we have positive gradients there. Now remember, the gradients are increasing as we go that way. We just saw that, so the graph must show that. So very gradually we have an increasing gradient there. Okay, so whether you're doing it by hand or verifying with technology, that's the way we'll roll. Now type 3. So when you see it, you think, what is that? Well, don't panic. We just need to rearrange that one. So if we have y dy dx plus x equals 0, we'd like to isolate the dy dx part. But how do we do that? Well, you may need to use more than one step. So we have to subtract x off both sides, and then to isolate dy dx we need to divide by y, and we'll have negative x on y. Okay, and we have a type 3, which you may note as that, or sometimes it's written as f of x g of y. Alright, but it is a type 3. And what we need to do then is perhaps you need to sketch a table, and because these are a little bit more sophisticated. Now, if you look at what we've got here, a table is a great way to organize it, so I would strongly recommend that. And that way you're seeing patterns and you're being thorough, so you can see that they've substituted from -2 through to +2 for x, and likewise for y, and we get answers there. Note how there is an undefined portion on this graph when we have y on the bottom. When that y is 0, we have an undefined situation here. We have some negatives and some positives too. Okay, but calculations for that are easy, and it's worth doing up a table in my opinion. And even before we cross to the graph, we can see some behaviors there. We can see that when x equals 0, apart from at the origin, which is a notable exception, we have 0 gradient. So if we cross over to a graph, you can see the 0 gradients there. Now the undefined portions, whoops, I didn't mean to put those stray blue lines there. You can denote them with a vertical line to denote that part of the field. Sometimes remember that is blank, so if you're reading from one, occasionally you'll see a void there, but you can see the behavior goes up, and it's sort of then it seems to be increasing, and then it's the opposite just above it. So at some stage it needed to have gone through the vertical, so you might see a blank portion there. The rest of it is really just those fields from the dy dx values from that table. Okay,